Welcome back to Algorithms and Uncertainty. In the last lecture, we introduced the definition of online set cover. We also introduced the LP relaxation, and this way we also have the notion of the fractional online set cover problem. And this is the precise problem that we want to solve today. Today we'll design and analyze an algorithm for this fractional online set cover problem. Once again, let's have a look how this is defined. This is this LP relaxation. So we have for each of the elements, we have a constraint that this element needs to be covered. And how does it have to be covered? We have these variables xs, which means by how much are we taking the set S. In the integral problem, these xs would have to be either 0 or 1. Now they can also be something like a half or so. Our objective is, of course, to minimize the sum of the cs times xs, where cs is the cost of the set S. Good. Further constraint, of course, is that these xs are all non-negative. But, as I was saying, they can, in principle, be fractional. How we are getting from a solution to this to an integral solution, this is what we will be talking about next time. What does now the online version of this fractional set cover look like? Well, at all times we are supposed to maintain a feasible solution x to this LP, or more precisely, to what has been revealed to us so far. And what does this mean? In the tth step, now we say that the tth element arrives, which means nothing but that out of these constraints, the tth one is revealed to us. And then we may only increase the assignment to the variables so that the constraints are fulfilled. So we are starting from an all 0 vector, and then we see one of these constraints, and we have to increase the variables so that this constraint is fulfilled. Of course, we still have the uncertainty that we don't know what other constraints will be revealed to us later on, or in the language of set cover, we do not know which future elements will have to be covered and how they can be covered. So it might be that we will, at this point now, or at a later point, actually regret our current decision, and we might say, oh, why did I set this variable to 1 and not that other variable to 1, or to a half, or whatever value. And so what one has to make sure is that ultimately you are happy or with whatever choice you made, or at least that it is a good choice at the point where you're at. Good. So we'll design an algorithm for exactly this problem. And then we want to show that this algorithm is no worse than some factor times the optimal solution to this LP. And this is the offline optimum, so the solution that is just adapted to this entire LP. So if you knew in advance what you'll have to cover, how would you cover things? And we'll do this via LP duality. And for this we introduced the dual LP of the set cover problem. This is a maximization problem. We'll have now a variable for each element, where before we had a constraint for each element. And now we have a constraint for each set that we can use to cover, whereas before we had a variable for each set that we can use to cover. And how does this now look like? Well, we have these ye variables, which are more or less, you can think of how expensive is it to cover element E. And now the way you can think about these constraints is you have this constraint here which tells you to cover all elements inside a set S, you should not spend more than CS. Why that? Because if you spend more than CS, then you could also take the set CS. So the set S which costs CS. And why is this now a maximization problem? Because it is it tells you, or what we're trying to find here is how much do we have to spend at least to cover everything while still maintaining these constraints. Good. And what we'll do is we'll also more or less solve this dual of the set cover LP. And how will we do this? We will make use of this lemma which we showed last time. We will, as I was saying, maintain this primal solution. This is what we call X superscript T, and P superscript T, this is the cost that we are spending or that we are incurring up to including time T. And this is the cost increase that we are incurring in step T. And this increase has to be bounded by beta times yt. Yt, this is by this we're keeping track of how much are we spending in step T. So if we had a beta equals 1 here, this would mean something like we're keeping in yt, we're keeping track of how much we are spending in step T, or how much we're spending at most in step T. We are introducing this factor beta here because this simplifies things for us a bit. And then we have this other thing, that namely that 1 over gamma times y should be dual feasible. And what's the point there? Well, we know that any solution y tells us how much you have to spend at least, how much even the offline solution has to spend. So we are now scaling down this y, and if this is dual feasible, then this gives us a lower bound on how much the offline optimum has to spend. And in combination, we are now getting to the point that if we have both of these things fulfilled, then we are beta times gamma competitive. And our goal today will be to design algorithms which make use of this lemma. And we'll do this first for the fractional ski rental problem. And then for this it is pretty easy because the LP has a pretty simple structure. You can only choose whether you buy or rent the skis on every day. So also there will be offline optimum and also the optimal dual solution. Those are really easy. And then we'll move to the more general set cover problem, for which we don't have the simple structure, but for which we can then still apply very similar ideas. And in both cases, we will obtain more or less the optimal algorithms for the respective problems. At least the algorithms are, well, for fractional ski rental, it is actually the optimal algorithm. For fractional set cover, it is the best known algorithm, and to some extent it is also the best algorithm. But let's first start with fractional ski rental. Let's now talk about fractional ski rental. Once again, this is the LP that we're now trying to solve online. This is its dual. So And every day we have to now set the xbuy and the xrent variable. So the xbuy variable, this might already have some value, so which means we might have bought like half of the skis, which means we only have to rent half of them. And of course we can only increase the variables at all times. The way we're thinking about this is that only the number of days is unknown, so at any point in time it can happen that just everything stops. And at that point then we have to be good. But fortunately enough, our way of phrasing this duality theorem or this lemma that we introduced last time, this is just totally fine with this, that we can just stop at any time. So we assume that we just don't know the number of days in advance. Good. Now this is the LP that we're trying to solve, being revealed one constraint at a time, and this is its dual. What does this dual mean? We have to make sure that overall, or what does the optimal solution do? The optimal solution does the following. It doesn't spend more than B overall, and it doesn't spend more than 1 per day. And this is what we want to come close to. Of course, this is something that we cannot achieve, although we haven't shown it for the fractional relaxation, but via more or less the same argument you can show, okay, here you certainly have to be worse than 1 competitive. So we cannot get exactly to what the optimum does, but we want to get as close to this as possible. And we want to do this by not only constructing a primal solution, but also constructing a dual solution simultaneously. And the dual solution that we will be constructing is indeed even the optimal dual solution. Namely, what does the optimal dual solution look like? It looks as follows. So how much is the optimum spending per day? Well, for the first capital B days, the optimum is spending 1, and afterwards the optimum is spending nothing. Well, this is not exactly true, so you might just say if there are more than B days, then at some overall you'll be spending B because you're buying the skis. And let's now, for simplicity or for concreteness, look at this optimal dual solution, namely that we're spending B split over the first B days, but we're spending only 1 per day, because for every day it shouldn't be cheaper to rent the skis than what we are doing. Good, so this is what we're doing in the first B days. So either there are fewer than B days, which means exactly we're just renting the skis in each of the days, or there are at least B days, in which case we buy the skis. Well, ideally we would buy them on the first day, but then we split the money over the first B days, and then afterwards we are happy. And now what we want to do is we want to design an algorithm for the fractional set cover problem, for the fractional ski rental problem, which does more or less the same thing. So we allow ourselves to spend not only 1 unit of money, but a little more, namely beta units of money on every day for the first B days, and afterwards we don't allow ourselves to spend any further money. And if we are able to do this, then we immediately get that our algorithm is beta competitive, just because this is the dual solution that we can apply in this lemma. Good. How do we do this in more detail? So we'll design a primal-dual algorithm. And the primal increase has to be bounded by, how would we write this? Let's use this p notation again. pt minus 1. This should be no more than beta times yt. Good. And as I was saying, using this optimal y, from above, property b is fulfilled with gamma being equal to 1. Now what can we derive from this property A? We'll need that in a step t, which is greater than b, we will need that pt minus 1 will have to be bounded by beta times yt, but yt, how much is the optimal solution spending there? They are not spending anything, so the primal increase has to be 0. And what does this mean? This means that our algorithm will have to make sure that the skis are already bought by time b. So what we'll need is that xt buy is already equal to 1. And what else do we need? In a step before that, we will need that the buy plus the rent variable is at least 1. And how can we achieve this? We can say that we set the rent variable to exactly the gap between 1 and the buy variable. So this is guaranteed if we set x rent t to be 1 minus the by variable. Good. Now what else do we need? We'll now have to have a look at the primal increase. How big is the primal increase? In step T? Well, this is what we call PT minus 1. And this we can write as capital B times x by t minus x by t minus 1 plus x rand t. Why that? Well, first of all, we are renting the skis by this amount, by the amount by which we have not yet bought them. We've bought like half of the skis or 3/4 of the skis or whatever. And more precisely, before this step, we had already bought like half of the skis. Now we are buying, say, an additional 1/4 of the skis, which means that this primal increase will be how much? We are buying an additional 1/4 of the skis, so this here will be, for example, 1/4. Let's assume we had already bought half of the skis, so we now have 3/4 of the skis. So what is left is 1/4 of the skis, so we are also renting 1/4 of the skis. And the question is now, the only question is, how much of the skis should we buy in each of the first B steps? Afterwards, we have to make sure that the skis are already bought, just because there our primal increase has to be 0. But what do we need for the earlier steps T? Well, for our condition to be fulfilled, this will have to be at most beta times yt. And how do we make sure that this is true? Well, we will simply set it so that we have equality. So this is guaranteed if we set beta times x by t minus x by t minus 1 plus x rand t superscript t equal to beta. And we can now plug in the definition of x rand t, which we had derived here. So we'll have that x by t minus x by t minus 1 plus 1 minus x by t, and all of this will be equal to beta. Good. How do we get there? Well, let's see. We will need that b minus 1 times x by t minus b times x by t minus 1, and this is equal to beta minus 1. x by t has to be equal to beta minus 1 over b minus 1 plus b over b minus 1 times x by t minus 1. So this here, this is supposed to be a beta, and this here, this is supposed to be a beta, and this is supposed to be a b. Good. So we want this recursion to be fulfilled. And we also want to make sure that after the bth step, we have definitely bought the skis. So let's first solve this recursion. We can see that x by t, how big is this? We're getting beta minus 1 over b minus 1 plus some factor times the previous value. And if you now do the math here, you can just do this on your own if you like, then you'll get to the following point. You get the sum of all these factors, b over b minus 1 to the power of t prime, summing from t prime from 0 to t minus 1 times beta minus 1 over b minus 1. And now you can solve this using, because this here, this is just a geometric sum, so we can just use the formula for this. So this is 1 minus b over b minus 1 to the power of t divided by 1 minus b over b minus 1, and all of this we multiply still by beta minus 1 divided by b minus 1. And this is now exactly equal to beta minus 1 times 1 minus b over b minus 1 to the power of t. Good. So there's nothing really spectacular happening in these steps. Once you get to this recursion, you can just solve it. This is, I think, nothing. I can show you really in detail how to do this. This is something you might want to do yourselves to really convince yourselves. Now, what was the further constraint that we wanted to make to ensure? We wanted to ensure that by time b we have bought the skis, because afterwards the dual solution isn't spending any further money, so neither should we. So this gives us that this x by variable at time b should be equal to 1. So we have that beta minus 1 times 1 minus b over b minus 1 to the power of b, this will have to be equal to 1. So, what can we do? We can set beta to be equal to 1 minus 1 over b to the power of b to the power of negative 1. And this here, this is something that is at most 1 minus 1 over e to the power of negative 1, which is approximately 1.58. Good. So, where are we now? We now derive that if we set beta to this quantity and use this formula here for the x bivariables, we have the following. We now have that on the one hand, the primal increases in the first b steps are bounded by beta. If we set the rand variables to what is still missing from the bivariables. And also, for the later steps, for every step after step b, we are at a point at which the bivariable is already at 1, so it doesn't have to be increased anymore. Good. So, we actually, with this dual LP solution, our lemma is now fulfilled with this particular beta and gamma being equal to 1, because this is already a feasible solution. Which means that overall, we have a beta competitive algorithm for the fractional ski rental problem. And this beta, how big was this? Beta was this weird quantity here. And this is like 1.58. Or e over e minus 1. Good. So, actually solving this fractional ski rental problem is pretty easy once you know that how much are you allowed to spend on any day. Once again, if there are fewer than b days, then this is totally fine because you are spending beta units of money on every day, whereas the optimal solution is spending 1 unit of money on every day. If there are more than b days, okay, then also everything is fine, because also then on the first b days you are spending beta units of money, and the optimal solution is spending b units of money. So in total you are spending beta times b, the optimal solution is spending b units of money. So there is no case in which you are worse than a factor b away from what the optimum does. And this is generally the spirit that we'll also apply to then now solve the fractional version of the set cover problem, although there things are more complicated because we cannot just as explicitly write down the optimal dual LP solution as we did it here. So we are not even aware of how much money are we allowed to spend per day. But fortunately enough, there are still some similar thoughts that we can apply there. Now what I want to do is I want to move slowly towards an algorithm for this fractional online set cover problem. And what I want to do is I want to apply more or less the same approach that we used for the fractional ski rental problem, although we don't actually know the optimal dual solution. But what will this now look like? So when we are in the tth step, we now assume that element t arrives. So we observe a new constraint which requires us that the sum of the xs, where s are all sets that contain t, that this has to be at least 1. This is happening in the primal LP. And what we now do is we have to define xt so that this constraint is fulfilled. And we are allowed to only increase from xt minus 1. And we will set some yt, which is a new variable in the dual LP. So how do we do this? What should we do? Well, fortunately enough, there are only two cases that can happen. Namely, either our yt minus 1 already fulfills this constraint. Well, then everything is perfect. We don't have to do anything. Why should we increase our variables if this constraint is already fulfilled? Which, by the way, corresponds to nothing but in the ski rental problem that there is an additional skiing day, but you've already bought the skis. Then also the constraint is just already fulfilled. So the other case is that for this yt minus 1, this sum here is strictly less than 1. And in this case, we will have to increase the variables in some way so that we get a feasible solution. So, case 1, as I was saying, is the trivial case. That the sum of these xs for t minus 1 are already at least 1. Then there's nothing to do. And we set xt equal to xt minus 1, and this yt we set to 0. And then there's the other case. But so far, we had something that was strictly less than 1. And what are we now doing? We will increase this xt minus 1 to xt, and we will account for the increases So for the increased cost, we will account for in the new variable, the new dual variable that we're setting. In the case of ski rental, we had a pretty explicit formula to do this, and we derived this just in an easy way because we knew what would be a good choice of this yt. Now we don't know how to set this yt ideally. But what we're doing now is something similar. We will just slowly increase these x variables. At the same time, we're also increasing y. We're increasing them by about the same rate. And how do we split up the increases of the axis? Because there are many variables that we might increase. Well, we use that. We use how big they already are up to this point. Let's have a closer look at this. So what we'll do is we'll increase x starting from xt minus 1, and we'll do this in continuous time. And we of course only have to do this up to the point where the sum of the xs that for the sets S that contain t is equal to 1. So as long as this is strictly smaller than 1, we have to keep increasing. So what we'll now do is we'll increase xs by a tiny bit. Let's call this dxs. And we'll increase yt by dy. And to avoid any confusion, maybe you've seen this notation before, maybe you haven't. So this is not d times xs, but the increase in xs. So this just means dxs, which is an infinitesimal increase in x. So you could also call this like delta xs. But because we are in this infinitesimal regime, we're actually choosing only a tiny bit. And eventually what we're doing is actually taking a limit so that the increase is going to 0, and we're doing infinitely many increases in like continuous time. Good, so this is what we want to do. And what is it that we want to make sure? We still want to make sure that this dual increase here reflects the cost, the primal cost increase. And how big is this? Well, how big is the primal increase? Well, if we now increase each of the xs by dxs, then the primal increase will be taking the sum of all s, for which t is contained in s, we'll have cs times dxs. By the way, there's really no point in increasing variables of sets which do not contain t, because they really don't help us to cover element t. Good. So for those that cover element t, we say, okay, increase each of them by dxs, and then this will be our primal increase. We're just doing this by a tiny step now. Now, how big is the dual increase? Well, the dual increase at the same time is dy. How big is dy? Well, the funny thing is, we can now say that this is at least by how much is element t covered so far times dy. Why is this? Because element t is not yet fully covered. Good. So this is the dual increase. Now we want these two things to exactly match. And how do we do this? Well, we'll have to just set this much here, this increase, to, so cs times dxs will have to be exactly equal to cs axis times dy. Or, written differently, if we set dxs to xs over cs times dy, the increases match up. Okay, so this is what we want to do ideally. We want to increase in continuous time the variables, the primal variables and the dual variable. And what we'll eventually do is exactly the following. Keep increasing the dual variables, keeping track of the primal variables via this formula, up to a point where you reach a feasible solution, meaning that also element t is covered. There's only one caveat, namely this xs initially is 0. And initially all of them are 0. So this doesn't actually quite work. So what we'll do instead is the following. Because initially xs is 0, we'll set instead dxs to 1 over cs times xs plus eta times dy, where this eta is tiny. And if you now look at this, what you'll see is, okay, this is actually just a differential equation. So one way to do this more precisely would be to say, okay, this is actually just a maybe somewhat big increase, and now we make the increase as small as possible. So we take the limit of this increase in y going to 0, then we'll get to the derivative of by how much we should increase xs. And so the solution of this differential equation is that xs will be some c1 times e to the power of c2 times y plus c3. So these are capital C's, which tell us, so this will what a general solution to this differential equation will look like, and we'll still have to figure out what C1, C2, and C3 are. And how do we do this? Well, if we take the derivative of this thing, then we'll see that we are getting capital C2 times capital C1 times e to the capital C2 times y, which is nothing but C2 times x s minus C3. Good. So, how big will these things have to be so that this is exactly this much? Well, this C3, this will have to be minus eta. The C2 will have to be 1 over CS. And what else do we have? We'll have to have that initially, this is all, we are starting from, if y is equal to 0, then we are starting from xt minus 1. So what we're getting here is that C1 will have to be x as at point t minus 1 plus eta. So if you now do all the math here, then you're getting to this formula. That axis at point t plus eta will have to be e to the power of 1 over cs times yt, and this is multiplied by xs at point t minus 1 plus eta. And how do we want to choose this yt? We want to choose this yt so that we're getting a feasible solution. So yt is the smallest value such that xt is feasible. Maybe you are a little confused now. How did this work? How did we get here? Well, that's totally fine. What we'll do next is still write down a complete algorithm and then once again analyze this algorithm. But what I wanted to show you is that this algorithm doesn't actually come out of thin air. There's like 2 steps here where we take a bit a leap of faith. Namely, why do we set exactly the increases like this? We could also choose them, define them in a different way. This would totally be fine. But if you do this, and then if you go through these steps here, then you get to this formula. And this is what is crucial now. We will only have to understand what happens if we use this formula. How big would we want to choose eta? So that, and then if we choose eta big, would this mean that we are, if we choose it too small, then, or if we choose it to be 0, then we will never get beyond 0. So then these yt will be huge if we choose eta too small. If we choose it too large, then there's nothing really happening here. So this is a question that we still have to see. How should we choose this eta? And indeed, what we'll see is that if we choose it to 1 over n, to be 1 over n, then everything works out fine. And this is what we'll do next. We will next analyze an algorithm which is based on exactly this formula, and we'll analyze this via our primal-dual lemma. Good. So now, finally, we can come to our algorithm for the fractional online set cover problem. And we'll use exactly the formula that we derived from in a maybe somewhat mysterious way from this primal-dual lemma. But even if you couldn't follow these steps of how we derived this, now we will once again write down a full algorithm and we'll analyze this. So what does our algorithm look like? Well, we will set eta to be 1 over n, and we will initialize all axes to be 0. And now in the tth step, what will happen? We, of course, observe the constraint saying that this element that just arrived has to be covered by at least 1, and we are getting also a dual variable yt. And now what we'll do is for each set S that contains element t, we increase axis from axis t minus 1 to axis t by the exact formula that we were given. Say axis t plus eta should be equal to this factor times axis t minus 1 plus eta. And yt should be the smallest number such that the sum of the s such that t is in s acts as t is at least 1. Good. So once again, we are increasing our variables. We're increasing them in more or less a multiplicative way. So variables that are already high are increased by more than variables which were not so high so far. And this is exactly expressed in this factor here, although we have this tiny ADA thing which which is used so that we don't start at all, we don't get stuck at all 0. Good. By the way, n, what was n? You might be now confused. N, this was the number of sets that we have to cover the elements. We also had m, which was the size of the universe. And now we have the following theorem. We will be showing that this algorithm is O of log n competitive. Good. How do we prove such a thing? Well, what we'll do is we'll verify the primal-dual lemma with beta being equal to 2 and gamma being equal to ln of n plus 1. So we still have these properties A and B. What were these properties? The first property was that the primal increase is bounded by beta times the dual increase. And the second property was that this dual thing that we're constructing is within gamma. If we scale it down by gamma, then it will be a feasible solution. Let's first talk about property A. So what is it that we claim here? We'll claim that pt minus pt minus 1, so this is the sum of all s, so that the cs times x as at time t minus x as at time t minus 1, this is supposed to be at most beta times yt. And what we'll now apply is how big is this increase? Well, for every s where t is not in s, we have that this thing here is simply 0. And if t is in s, then things are more interesting. Then, how big is x as t? Well, we had our formula. This was our formula. So we can also write this in terms of x as t minus 1 plus eta. This is nothing but e to the negative 1 over cs times yt multiplied by x as t plus eta. And if we now see what we're getting here, this means that x as t minus x as t minus 1, this is exactly equal to x as t plus eta minus x as t minus 1 plus eta, so adding and subtracting eta. And now we can say, okay, this is x as t plus eta minus e to the power of negative 1 over cs times x as t plus eta. So this is equal to 1 minus e to the power of minus 1 over cs times, oh, I think I forgot the yt here, times x as t plus eta. Now this here is nothing spectacular. We can just use that this is at most 1 over cs times yt. This is just a standard formula coming from the concavity or convexity of this function, depending on, so eventually it's just the convexity of the exponential function that we're using here, or the concavity of 1 minus e to the negative x. Good, so there's nothing really spectacular about this step. So, where are we getting with this? We can see that we have that the increase of x as t is at most its value afterwards plus eta times yt. So, the primal increase is how much? This is pt minus 1. This is at most taking the sum over all s such that t is in s, cs times x as t minus x as t minus 1. Okay, this is even, we could even write here that this is equal to this. And for this, we now have an upper bound. So we can now say that this is at most take the sum over all s that contain t, cs times 1 over cs times x as t plus eta times yt. And how big is this? Well, this is, I get here that these things nicely cancel. So this is the sum of the x-s times yt plus the sum of the s that contain element t, just taking the sum of all eta. This here, this will be equal to 1 because we must increase the xs exactly so that the new element is exactly covered by 1. And what do we have here? Well, we just have at most n times eta, so this is equal to 1. So overall, this is at most 2 times yt. So what happened here? One crucial thing was that the increases of more expensive sets are less. This is somehow the magic that is already inside our formula. Our formula said that here the increase of a more expensive set is less, or this factor is less for a more expensive set than it is for a cheaper set. And this is why this here cancels. So it's not that we say, okay, expensive sets we don't use at all, but we use something like, almost like, the increase is proportional to the cost. Good. And then what else do we have? What else is crucial here? Here, at this step, we use that we do not increase the variables by more than what is absolutely necessary. So recall that in our algorithm we said, okay, the yt is chosen to be the smallest number such that we get a feasible solution. And here we use that this eta is small enough. And overall we get that the primal increase is at most 2 times the dual increase. Good. Now we'll have to also show the other part, namely, this is property B. We will have to show that 1 over gamma times y is feasible. How do we do that? So what we will consider any set S, and we will have to show that the sum of the t in S 1 over gamma times yt, that this is at most the cost of that set. Why is this true? What did our algorithm do? If t is contained in a set S, then what do we know about yt? Yt we can write as cs times ln of x as t plus eta minus cs times ln of x as t minus 1 plus eta. This is just, again, the formula that we use to increase the xs, but now, of course, solved by yt. And what happens if t is not in S? Then we'll have that x as t will be equal to x as t minus 1. So this means that we have something similar, so then 0 is equal to ln times xs plus eta minus cs times ln x as t minus 1 plus eta. Good. So what does this tell us? If we take the sum over all t that are contained in a set S, how can we write the sum of the yt? Well, we might as well take the sum over all possible t and then always add up this cs times ln xst plus eta minus cs times ln xst minus 1 plus eta. Why is this? Because we can just add up all these, then we have everything that contains t in S, and then let's also add all of these because all of this thing here is 0 anyway, so then we can just sum up these terms over all possible t. Good. And now we are getting here a telescoping sum, and this simplifies our life because now what we're getting here is that this is xs m plus eta divided by xs0 plus eta. And furthermore, xsm will be at most 1, xs0 will be equal to 0. So the sum of these t and s, of these yt, this is no more than cs times ln of 1 plus eta divided by eta, and this is cs times ln n plus 1 by the definition of eta. And this is exactly gamma times cs. And this is, I think, what we claimed before. Yes, this is what we claimed right here. If you multiply this inequality by gamma, then this is exactly what we came up with here. Good, so this concludes today's lecture. We now have derived an O of log n competitive algorithm for the fractional set cover problem, or the online fractional set cover problem. How did this work? We used this primal-dual construction. The algorithm itself is maybe not super straightforward, so let me once again go back to the algorithm. The point is we have these multiplicative increases and we want to increase each of the dual variables so that the increases are somewhat proportional by how big the variables are so far, and also sets that are more expensive, for them the increase is smaller than for expensive sets. And the key idea was to keep track of this yt, to choose this yt as small as possible, so that you never actually exceed 1. And then this yt, just by this construction, makes sure that an offline optimal solution cannot be much better than this, because at all times these yt, those actually encode an almost feasible dual solution, and the offline optimum cannot be much better than this dual solution. This is a super great algorithm template that you can also use for other problems. This is something we'll talk about next time, and also we'll talk about the question, how can we actually obtain an integral solution. Okay, it's great that we now are able to solve this fractionally, but eventually what we were interested in was that we take each set we take each set or we don't take it. This is something we still have to talk about. We will use randomized rounding for this, but we will have to be more careful than in offline settings where you might have seen randomized rounding, because here we don't actually know in advance where our entire LP solution and so on. So this is exactly what we'll be talking about next time. I hope that you enjoyed watching this video. You watch also the next video. If you have any questions, please do reach out to me, and see you next time. Stay safe. Bye.